So this is week 5 of the thermodynamics course. Uh, so till now we have seen uh, the started with zeroth law and so on basics, and then with first law. So again today and the next week we'll continue solving problems on first law for a system, and then go through a flow systems and so on. So this week again we'll have some problems on first law, considering applying first law to a system, evaluating that uh, system, heat interaction, work interaction, so on, and to calculate those and for ideal gas mixtures. And again will continue again with two phases and so on. So let's start for today. So starting with first question, consider a closed system of constant volume containing wet steam. The objective is to study the evolution of the thermodynamic state of water during heating from the initial temperature T1 to the final temperature T2. This can determine the specific volume, the specific internal energy, and the specific enthalpy of the initial state 1. Determine the specific volume, the pressure, the specific internal energy, and the specific enthalpy at the final state 2. Then calculate the received specific heat energy during heating. So these are being asked. So what to break it down, we have a constant volume system or a closed system, a rigid vessel in which it has a wet steam. So we need to see how this steam changes its state, or what happens to the steam. So we are heating it. So initially this is at the temperature of T1 and finally it is at a temperature of T2. So determine the specific volume. So what the properties we need to calculate. At the start is a specific internal energy, specific volume, and specific enthalpy at the start. And similarly at the state 2. And we also need to find out what is the heat energy which is being supplied. So what do we know? The initial pressure is 20 bar, and the dryness fraction is or vapor fraction is 0.5. And what we know is the final temperature is 450 degrees Celsius. So initially it is at 20 bar and 0.5 degrees Celsius, and the final temperature is 450 degrees Celsius, and the data is also given directly. So here the table for 450 degrees Celsius superheated steam condition is given for pressures of 58, 60, 62 and 64, and the corresponding specific volume and specific enthalpy. So enthalpy is still yet to be taught, so we'll look at just U and saturation states for pressures and temperature, and similarly for that. So enthalpy is internal energy plus P times V, that is enthalpy. So the specific volume and specific enthalpy are calculated. So it's just how you calculate internal energy, you calculate the other properties. So your saturated liquid specific volume plus the change in volume between saturated vapor and saturated liquid multiplied by the vapor fraction. So that will give you the vapor fraction at any point x. So V1 here, we know it is at pressure of 20 bar and dryness fraction of 0.5. So we'll corresponding to 20 bar, we'll take the saturated liquid and saturated vapor specific volumes and enthalpies and calculate at state 1 what will be the corresponding specific volume. So that comes out to be 0.05036 meter cube per kg. So this is a wet steam. So you have both vapor as well as liquid. So if you see the volume 0.05, it is lie between V dash and V double dash. So you have V double dash is fully vapor, saturated vapor, which is 0.099, sorry, liquid. And sorry, V dash is liquid, so you have 0.0011766. That's the specific volume of liquid. And V double dash 0.09995. So that lies between these two, V1. And similarly, H1 will come out to be 1852.9. And U1 is H minus PV. So substituting that, we can find an internal energy, which is 1752.2 kilojoule per kg. So now what we know is that during the process of heating, my volume is constant. So whatever my final volume is, it will be equal to the initial volume. Or and since the mass is not leaving the system, so your mass is constant in the system, your specific volume will remain same. So your mass is constant and your volume is constant. So that in terms says that your specific volume is constant. So you can take specific volume to be constant. So V2 is equal to V1. So which is equals to 0.05036, which we found. So substituting for 450 degrees Celsius, we get by interpolation, we will find that your for corresponding to this specific volume, you're going back, it will lie between 62 and 60. So it will come out to be 61.9. You can do it by interpolation and you'll find the pressure and enthalpy. With that, you can find out the internal energy, which comes out to 988.8 kilojoule per kg. So next is the second part of the question was to find out how much heat has been supplied. So heat is the change in internal energy. So apply first law for the system. So there is heat coming in, and there is no work transfer. So work transfer will be 0. So whatever heat is supplied, it will be supplied to raise the internal energy of the system. So Q is delta U. That's what is written. And so Q will be the change in internal energy, which is 1236.6 kilojoule per kg. So this is positive, so it is supplied to the system. So next is a closed rigid tank filled with water vapor, initially at 20 megapascal, 520 degrees Celsius, cooled until its temperature reaches 400 degrees Celsius. Using the compressibility chart, determine the specific volume of the water vapor in meter cube per kg at the initial state, the pressure in megapascal at the final state. So compare the results of part A and B obtained from superheated vapor table. So the first case is your critical temperatures are given. Water vapor, so it is for water it is 647.3 Kelvin and pressure is 22.09 megapascal, the critical pressure. So with that, the reduced pressure will come out to be 1.23 and reduced pressure is 0.91. So from the chart, the Z value here at 1 is 0.83. So using that, Z is P1 V1 by RT1. So since we know from compressibility chart the value of compressibility factor, we can estimate the volume. So volume is 0.83 times 8.314 into 10 power 3 multiplied by your temperature, 793 Kelvin, divide by, because initially it is at 520. So 520 plus 273, you get 793, divide by the pressure and the molar mass, so which you get specific volume to be 0.0152 meter cube per kg. So for this condition of pressure and temperature, if you find from steam table, it comes out to be 0.01551, so which is pretty close. So next is the second state. So for that, the similar approach. So we get V dash is to be 1.12, and at state 2 your temperature ratio is 1.04. So from using the compressibility factor and 1.12 and the temperature ratio of 1.04, we can estimate the pressure ratio. So that comes out to be 6.69. So multiplied by the initial critical pressure, so that gives you the final pressure 15.24. So moving on to next question. We have a rigid vessel, initially contains 1 kg of saturated R134A vapor and 15 kgs of saturated R134A liquid at 900 kilopascal. So a relief valve is provided on the top of the vessel in order to maintain the pressure inside the vessel constant at 900 kilopascal by allowing saturated vapor to escape. So heat is now added to the vessel until all the liquid evaporates. So determine the mass of vapor that escapes, and B, the heat supply. C, also determine, so C part is not required, we will solve A and B. So just edit. So what we know is there is a rigid vessel. So it contains 1 kg of vapor, saturated vapor of R134A and 15 kgs of saturated liquid R134A, and this whole two-phase R134A is in a pressure of 900 kilopascal. So in terms of bar, it's 9 bar. So a relief valve is provided on the top of the vessel in order to maintain the pressure inside the vessel constant at 900 kilopascal. So what is done is by allowing saturated vapor to escape. So you are adding heat. So what will happen is your both pressure, since the volume is constant, your both pressure and temperature will rise. So to keep the pressure constant, now you need to remove some saturated vapor. You are reducing mass. So some amount of saturated vapor is left out. So your pressure is maintained at 900 kilopascal. So this process is continuous. So this heat is added until all of the liquid in the vessel evaporates. So you have only saturated vapor left, but the mass is now different. So determine the mass of vapor that escapes and the heat supply. I think this has to be okay. That requires it's a flow system. So we'll come back to that question again. So this one is a closed rigid tank contains 5 kg of air initially at 300 Kelvin and 1 bar. So as illustrated in figure, the tank is in contact with a thermal reservoir at 600 Kelvin, and heat transfer occurs at the boundary where the temperature is 600 Kelvin. So a stirring rod transfers 600 kilojoule of energy to the air. The final temperature is 600 Kelvin. The air can be modeled as an ideal gas with CV of 0.733 kilojoule per kg Kelvin, and kinetic and potential energy effects are negligible. So determine the amount of entropy entropy. So we have two insulated tanks, A and B are connected by a valve. Tank A has a volume of 1 meter cube and initially contains argon at 300 kilopascal and 10 degrees Celsius. Tank B has a volume of 2 meter cube and initially contains ethane at 200 kilopascal at 50 degrees Celsius. The valve is opened and remains open until the resulting gas mixture comes to a uniform state. So determine the final pressure and temperature. So we have two insulated tanks, and in one tank we have 1 meter cube volume and contains argon at 10 degrees Celsius and 300 kilopascal, and in another tank we have ethane which is at 200 kilopascal and 50 degrees Celsius. So now these are two tanks are connected by a valve, and when the valve is open, these gases are allowed to mix, and at the final state what happens is we have a uniform mixture which is formed and a uniform state has formed. So what will be the final pressure and temperature? So first case, if you put a control volume for this for tank A and B, and if you apply first law, so what you can see is there is no work which is being done and there is no heat transfer which is happening. So what will happen is your internal energy is now constant. So whatever change in internal energy is happening, so that is gained by the other or lost by the one. So the total change in internal energy will be 0 for both the tank contents in the tank. So U2 minus U1 is equal to 0. So if you write in terms of the gases, individual gases, initially the argon is at temperature A1, which is in tank A and 1, and it has come to a temperature T2. Similarly, ethane, which was initially at temperature B1, which is at tank B and state 1, it has come to a uniform state temperature T2. So m times Cv into delta T for both argon and ethane. So first we need to find out the mass of the individual gases. So initially what we know is tank A has volume of 1 meter cube and tank B has a volume of 2 meter cubes, and we know the pressures and temperature. So using this we can find out the masses. So applying ideal gas law, so mass is PV by RT. So for argon the initial pressure is 300 kilopascal, so 300 volume is 1 divided by R, for argon is 0.2081 multiplied by your temperature, which is 10 degrees Celsius, so 273.15 plus 10, you get 283.15 in Kelvin. So substituting this we get kilopascal, there is 10 power 3, and here also R is in kilojoules, so that gets cancelled out. So what we will get is 5.0913 kgs. So that is the mass of argon which is there in tank A. And similarly for ethane, so your mass is again by ideal gas law PV by RT. So substituting the values, your pressure of 200 kilopascal, volume of 2 meter cube, and your R is 0.2765 and 50 degrees Celsius, so 273.15 plus 50 will give you mass of ethane to be 4.4767 kgs. So if you apply the mass balance, so for initially individually argon and ethane are present. So now once the valve is opened, they form a uniform mixture, but still your mass will remain same. So the total mass now is 9.568. So the sum of individual. No, is there any doubt? You have any specific doubts?
No, sir, no, I don't have any doubts.
Okay.
I thought there was someone else in the call. That's why I asked.
No, no.
Sir, may I know your good name? Actually, if I have some other doubts while solving, maybe I can ask you then.
Yeah, yeah. My name is Bharat.
Okay, so can I get any sort of contact information so that I can ask you?
No,
Or
no. You
just,
see this relevant to this. You can put it in the discussion.
okay, in the discussion group itself.
Yeah.
Oh,
If there are
okay,
other
great.
TAs or persons who look after it, or even I can help you there.
Okay,
Or in the
okay,
sessions, if
not
you have any
always will
doubts, you
be.
can bring those doubts.
Okay,
Apart from
okay,
assignments, you can bring those. So we'll help you in those.
okay. And not all the sessions will be taken by you, right?
No, no. This all the 12 weeks, the problem solving session will be by me.
Okay, okay.
The
So,
problem, this one will Tuesday 6 o'clock. I'll take.
okay. And one more small doubt.
Yeah.
This problem solving which you're solving, will there be any sort of notes which will be available in the future? Because
Yeah, yeah. I have to upload this in a folder. I'll do so.
okay,
Yeah,
okay, it's great. So thank you so much. No, because
yeah,
I'm not able to attend the meet now. That's why I thought I'll
yeah.
just
Sure, sure. No issue.
hop in the meet.
This recording will also be available, and the say slides will also be. I'll be uploading those.
In where, sir? Where
They
will you
in the
upload
same
those?
Google sheet which is floated in the core section, right? There will be
No, sir,
section.
I don't know where that is.
No, where you see the videos, right? In the
Yes, sir.
NPTEL, you will have a
Yes.
session there, problem solving or live session something. So if you're
Okay.
there,
In
then
the
with
announcement section,
not in the announcement, but over the
in the
week,
discussion
the week
forum.
1, week 2, week 3, there will be
Uh,
at the bottom there will be some option. So if you click there, it will direct you to a drive link
okay.
for a Google Sheet.
Okay.
So that will
Okay.
contain all the links
Okay.
for recordings and the folder
Okay.
containing this.
Okay. Okay. Great.
Okay.
Okay, sir. Okay, sir. Thank you so much.
Yeah. So your mass, since the volume is, we have a closed system, so your mass will remain same. So the total mass after the formation of uniform state is 9.568.
5 minutes? Sorry, sir. Sorry, sir. I
Yeah, so
forgot
no,
to
no. Uh, so your mass is 9.568. So substituting this in the delta U equal to 0, since there is no heat transfer, there is no work transfer. So your internal energy change from state 1 to state 2 will also be 0. So substituting in the equation, you will get, you can find out the final temperature. So now you know mass, you know the temperatures. So the final temperature comes out to be 315.5 Kelvin. So the mixture now, the resulting mixture's gas constant is summation of your mass fraction into the individual gas uh, constants. So the mass fraction is the mass of that gas divided by the total mass. So that will give you the mass fraction. So first one for propane, for argon is 5.0913 divided by the total mass 9.568 multiplied by the gas constant of argon, which is 0.2081, and similarly for ethane, which is 4.4767 divided by 9.568 multiplied by the gas constant of ethane, 0.2765. So for this and all, even if it's not given, in this case it's not given, so you can find it from the universal gas constant divided by the molar mass. So you'll straight away get that. So that will give you R mix as 0.2401 kilojoule per kg Kelvin, and your pressure for now, assuming this whole gases have formed a uniform state, so your pressures will be M2 RT2 divided by the total volume. So the total mass in the combined volume now is 9.568, and the total volume is 3 meter cubes, and the temperature of the uniform state we have found out to be 315.5. So and R is also, R of the mixture is also we have found out to be 0.2401. So we know all of the quantities. The only unknown is the pressure. So applying the ideal gas equation, we can find out the pressure. So it comes out to be, so P2 is M2 RT2 by volume, total volume. So substituting the values, we get P2 to be 242 kilopascals. So moving on, next question. So consider the system made of a receiver A and a reservoir B separated by a tight valve. So at the initial state of equilibrium 1, receiver A contains oxygen at the pressure P of oxygen at state 1, so PO21, and the temperature TO21, while the reservoir B contains nitrogen at the pressure of PN21 and the temperature TN21. The experiment consists in opening the valve and in letting the nitrogen flow into the receiver A until we get a mixture of oxygen and nitrogen whose composition is the one of air defined by the following molar fractions. So we have okay, and the final state of equilibrium, at the final state of equilibrium 2, this mixture is at a pressure of P2 and the temperature T2. So this is what is happening. You have two separate containers. One, there is a oxygen which is insulated, and there is a nitrogen which is connected through a valve, and initially the pressures and temperatures of each of the gases is given. So what happens is, when the valve is open, so nitrogen starts flowing inside the tank containing oxygen and it forms a mixture. So that is given by the molar fraction of 21 kilomoles of oxygen and 79 kilomoles of nitrogen. So what we assume is the reservoir B is very large in dimension, and that the thermodynamic state of nitrogen remains constant during the process. So it's like nitrogen is a reservoir, so that's what is being given. It takes from reservoir B. So taking some amount of nitrogen will not change the properties of the nitrogen inside the reservoir. So that's what a reservoir means. So you are taking, and it doesn't affect the reservoir. It doesn't, you take a small quantity, so it doesn't matter much. So the temperature and pressure will not change for the nitrogen reservoir. So the volume of gas contained in the pipe is negligible, and the reservoir A is thermally insulated, so there is no heat transfer, and the change of potential energy is negligible. And what we assume is oxygen and nitrogen are considered as perfect gases. So perfect gases, we assume that your Cp and Cv value doesn't change with respect to temperature and so on. So the starters, what we know is, initially the oxygen we can consider is what is given is the pressure is at 5 bar, your temperature is at 27 degrees Celsius. The molar mass, the mass of oxygen inside the tank initially is 2 kgs, and the nitrogen pressure is 50 bar. So if you see the difference in pressure, so nitrogen reservoir is at 50 bar, and so it flows inside the oxygen tank, and the nitrogen temperature is 117 degrees Celsius. So the molar mass of oxygen is 31.999, or you can assume it to be 32. Isobaric specific heat of oxygen is 0.9094 kilojoule per kg Kelvin. The molar mass of nitrogen similarly is 28.013 kg per kilomole, and isobaric specific heat of nitrogen is 1.03888. So we know this. So what is to be found out? Calculate the final temperature of the mixture, calculate the final pressure of the mixture, calculate the partial pressures of the constituents of the mixture at the final state, calculate the partial volumes of the constituent of the mixture at the final state, calculate the change of internal energy during the process. So it's not been covered. So calculate the change of internal energy of the during the process. So start with, we'll first find out what is the gas constants of each of the gases. So for oxygen, so we know the molar mass and we know the universal gas constant. So R is universal gas constant divided by the molar mass. So that comes out to be 0.2598 kilojoule per kg Kelvin. Similarly, for nitrogen, R is universal gas constant divided by the mass of nitrogen. So it comes out to be 0.2968 kilojoule per kg Kelvin. So since your specific heat, isobaric specific heat is given, so using this you can use it, you can find out isochoric specific heat, that is CV, can be found out. So Cp is Cv plus R, or Cv is Cp minus R. So for Cv of oxygen, it's Cp of oxygen minus R, your gas constant of oxygen. So that comes out to be 0.6496 kilojoule per kg Kelvin. Similarly, your specific volume of specific heat for constant volume for nitrogen is Cv of nitrogen is Cp of nitrogen minus R of nitrogen. So that comes out to be 0.742 kilojoule per kg Kelvin. Now we know that the gas forms a mixture of nitrogen and oxygen inside the tank, and we also know the composition in which it has been formed. So it is given the molar fraction is to be 0.21 and 0.79. So using that we can find out the total molar mass. Since molar mass here is in kg per kilomole, so you have to multiply it with the molar fractions. So the molar mass of mixture will be the molar fraction multiplied by the molar mass. So summation of that will give you the molar mass of the mixture. So we know the individual molar masses and we do individual molar fractions. So oxygen is 0.21 and similarly molar mass is 32 and 0.79 for oxygen, and the molar mass of nitrogen 0.79 for nitrogen, and molar mass of nitrogen is 28.013. So summing up, multiplying and summing it up will give you the molar mass to be 28.85 kilojoule per kg per kilomole. So the mass fraction of the constituents of the mixture are according to your molar mass of oxygen divided by molar mass of mixture multiplied by your molar fractions of oxygen. They will give you mass fraction. So mass is nothing but your mole multiplied by molar mass. So that's what is being done here. So that gives you 0.2329 kg of oxygen per kg of the mixture. So the mass fraction is 0.2329, and similarly for nitrogen the mass fraction will be 1 minus of this, or we can find out using mass or molar mass of nitrogen into mole fraction of nitrogen divided by the total molar mass. So that will give you the mass fraction of nitrogen, or straight away 1 minus the mass fraction of oxygen. Both will give you 0.7671 kg of nitrogen per kg of the mixture. So next is finding the specific constants for the mixture. So starting with the gas constant. So gas constant is summation of your mass fraction into the individual gas constant of the species. So 0.2329 into R of CO2 and 0.7671 into R of nitrogen. So it will give you 0.2882 kilojoule per kg Kelvin. So that is the gas constant of the mixture. Next is to consider the closed system to be reservoir A and the nitrogen that is in reservoir B at state 1, and that will be inside so what we are doing is, so if you go back to the image here, so we are applying a control volume. So in a control volume across the tank A where the oxygen is contained, and then the portion of nitrogen which will enter the oxygen tank. So this both we are applying a control volume. So in this case now this is like the previous problem where we did two gases which is getting mixed. So it turns out to be same kind of problem. So we are this is the nitrogen which will be entering in the oxygen tank. So that portion is again considered to be in the control volume. So it's just not to the tank but also the mass of nitrogen which is entering the tank. So that is the control volume which we are taking. So in that case what will happen is the change in internal energy of oxygen plus the change in internal energy of nitrogen is equal to the work received. So the work received will be, since pressure is constant, so whatever pressure is acting upon the nitrogen and the change in the volume of the nitrogen, so that is the work which is being done on the system, because it's compressing it to and pushing it inside. So this much amount of volume is getting displaced with the constant pressure. So your work done is P into V, so which is can be written as from ideal gas MRT. So substituting this, we get mass of oxygen into CV of oxygen and T2 minus T naught plus mCV delta T of nitrogen equals to the MRT for nitrogen which is getting transferred inside. So it comes out to be T2 is rearranging this. So this is the expression which we get. So T2 comes out to be 494.54, or in terms of degree Celsius is 221.39 degrees Celsius. So now we know temperature, we can find, we know the total mass, so we can find out the pressure. So we know initially the oxygen to be at 2 kgs. So we can find out the nitrogen using the mass fraction values. So mass fraction of nitrogen into mass of oxygen divided by mass fraction of CO2. So what we are saying is total mass is constant. So the mass fraction of nitrogen can be written as mass of nitrogen divided by the total mass of the mixture. So replacing taking the denominator to the other side and bringing down the mass fraction, this is what we get. So mass of nitrogen divided by mass fraction of nitrogen equals mass of oxygen divided by mass fraction of oxygen. So rearranging, this is what we get. So using that we can find out mass of nitrogen to be 6.587 kgs. So the volume of reservoir A is then initial condition of, with the initial condition of oxygen, we can find out the initial what is the volume of the receiver A. So ideal gas equation PV equals MRT. So volume will be mass of oxygen into gas constant of oxygen into temperature divided by pressure, which comes out to be 0.3199 meter cube. And so substituting this, we know mu MO2 2 kg, Mn2 we have found out 6.587. We know the mixture, gas mixture R, we know temperature, and we have found out volume, so we can find out pressure, which comes out to be 39.24 bar. So we have found out partial the total final pressure and final temperature. Next is we need to find out the partial pressures. So partial pressure is nothing but using the Dalton's partial pressure law. You can your molar fraction into pressure will give you the partial pressure. So P of oxygen is your mole fraction of oxygen multiplied by your pressure, the total pressure. So since it is asked at the state 2, so we'll use P2. So mole fraction is 0.21 for oxygen multiplied by 39.24. That gives you 8.24 bar. And similarly your nitrogen, so mole fraction of nitrogen into the partial pressure of the total pressure. So 0.79 into 39.24 gives you 31 bar. So similarly, you can find out partial pressure volumes. So that is mole fraction into your volume, the total volume. We give you the partial volumes. So VO2 is molar fraction into V2, so gives you 0.0655 meter cube, and similarly for nitrogen it's 0.2464 meter cube. So and change in internal energy is change in internal energy is with based on final temperature, so which we have already found out. The total change in internal energy is the work done. This MRT1 762.8 kilojoules. So moving on to next question. We have a 10-meter high cylinder cross section, 10-meter high cylinder cross sectional area of 0.1 meter square, has a massless piston at the bottom with water at 20 degrees Celsius on top of it, as shown in figure. So air at 300 Kelvin and volume of 0.3 meter cube under the piston is heated so that the piston moves up, spilling the water out over the side. Find the total heat transfer to the air when all the water has been pushed out. So what it says is, we have a 10-meter high cylinder. So this is a cylinder which the total height is 10 meters, and the cross sectional area of the cylinder is 0.1 meter square. So that is given. So that gives you the total volume of the cylinder. So that is indirectly given. And you have a massless piston at the bottom, and there is air at the bottom, and then the massless piston, and then you have water at top of it. So the water is at a temperature of 20 degrees Celsius. Now the air is at a temperature of 300 Kelvin. So this is 273 minus 300. So that is around 27 degrees Celsius. That is 27 degrees. So and the volume is, they say, is 0.3 meter cube. So that means your cross section area is 0.1 meter square. So multiply by 3 is 0.3. So you have 3 meters of air inside, and above that you have piston, and then the rest is water. So what is done is, now the piston is getting heated, the air is getting heated, and because air is getting heated, it gets more internal energy, and what it will do is it will try to push the piston up. So the piston will start moving, and in that process the water above it starts spilling over on the sides. So we need to find out what the total heat transfer to the air will be when all the water has been pushed out. So we'll see first. Initially there is a pressure which is exerted by air from the bottom. So doing an force balance here. So you have pressure of air which is acting from the bottom. So if you take a piston, you have piston here, and and there is a force which is acting from bottom, and, there is a mass weight of piston which is from the top, and again the mass of uh, the water which is acting. So what's happening is the pressure is exerted, and you have weight of piston, but this is being a massless piston, so the piston weight is negligible, 0. So there is only two forces which is acting. So one is the pressure exerted by the air, and the other is the weight of the water. So this two is balanced at any point. Uh, so there is initially a small change in pressure, so the water gets spilled and it will be balancing the two forces. If you take any instant of time, it goes very infinitesimally slow at any state. You say assume that it's a quasi-static process. So at any state, this force will be balanced. So the mass of water, the pressure exerted by that will balance the pressure of the air. So since the mass is reducing and the water is spilling, so this will keep on reducing over time. Since your area is constant, so the volume change is dependent only on the height of the water. So if you see, so the pressure is linearly varying with respect to the height of the water. So this is what it look like. So initially it will be at pressure P1 because of the total weight of the water which is exerted on the air. So it will be at initially pressure P1, and it will reduce since the mass is reducing, it will reduce, the pressure will keep on reducing, and it will reach pressure P2 when the air is at a total occupies the total volume of the cylinder, which is the Vmax. So that's the process which is happening. So first is we'll assume we'll find out what is the volume of water initially and what is the mass of the water which is present over the piston. So first is the water on top is compressed liquid and has a volume and mass of so volume of water will be total volume minus the volume occupied by air. The total volume is which is high, we know the cylinder height is 10 and the cross section is 0.1, so that comes out to be 1 meter cube minus the volume occupied by air which is 0.3 meter cube. So we can find out that the water occupied the volume occupied by water is 0.7 meter cube. So now since we know the volume, we can find out your mass. So mass of water will be volume divided by specific volume. So specific volume of water is 0.001002 meter cube per kg, and volume is 0.7 meter cube. So substituting, we find that the mass of water is 698.6 kgs. So the initial air pressure is then, so initially it will be at some pressure P0, which is atmospheric pressure. So here P0 is atmospheric pressure. So here what's happening is after water is all spilled out, so the pressure which is acting is the atmospheric pressure. So now in this first case, when there is no water spillage or the initial condition where the water is filled, so you have the pressure acting on the piston is the atmospheric pressure plus the pressure exerted by the height of the water. So P1 will be P0 plus mg your mass mg divided by area, or you can find rho gh, whatever, you will get the same. So we will get 101.325, which is atmospheric pressure, plus your mass of water 698.6 multiplied by G 9.807 divided by your area 0.1 divided into 1000 to convert into kilopascal, since your atmospheric pressure is in kilopascal. So that gives you 169.84 kilopascal. Now the mass of air which is present initially, so mass of air is PV by RT, assuming an ideal gas. So we know the pressure now, since both has to be balanced, So the pressure exerted by the air will be P1. So P1 is 169.84 multiplied by the volume occupied by air, which is 0.3 meter cube, divided by the gas constant of air, which is 0.287, and temperature 300. So that gives you the mass of air to be 0.592 kilograms. And the second state is when there is no water present and the piston is at the top. So the pressure now will be only the atmospheric pressure. So the pressure balance will be the pressure exerted by air is equal to the atmospheric pressure. So in the second case, we know the pressure, we know the volume is the total volume of the cylinder, which is 1 meter cube. So using this pressure and volume, my mass is same. So you can find out PV by T is constant for an ideal gas. So you can estimate the state T2. So P1 P2 V2 by P2 V2 multiplied by T1 divided by P1 V1 give you your temperature at the final state is 596.59 Kelvin. So that is the temperature. So so what is the work which is done? So work is done is the area under the curve. Straight away we can find out, or you can find out pressure, how the pressure is varying with respect to volume relation, and then integrating that will give you this again the same expression here, half P1 plus P2 multiplied by V2 minus V1. So that's the two approaches. So we know that this is varying linearly from P1 to P0. So that's a straight line, and we know the volumes, initial and final volume. So you can straight away find out the volume under this straight line, which is half times P1 plus P2 multiplied by V2 minus V1. So this comes out to be 94.91 kilojoules. So that is the work done from air expanding from 0.3 meter cube to 1 meter cube. So now in this process, what is the heat which is supplied? So to find out that, we will apply the first law. So first law is heat is mass into change in internal energy plus the work done. So for this is applying just for the air. So you get mCV delta T plus the work done. So mCV is mass of air, which we have found out, which is 0.592 into your CV of air, which is 0.717, multiplied by the change in temperature, which is 596.59, which is the final temperature, minus the initial temperature of 300, plus the work done, which we have found out 94.91 kilojoules. So this comes out to be 220.7 kilojoules. So the other way around is we can estimate the internal energies from the table charts for air. So that will also give you your value to be, your change in internal energy to be 218.14 kilojoule per kg. With comparing this with our calculation, it comes out to be 212.5 kilojoule per kg. So there is no much change, but this is with the assumption that it's an ideal gas and perfect gas and so on. So next question, we have a rigid tank A of volume 0.6 meter cube. So a very 0.6 meter contains 3 kg of water at 120 degrees Celsius, and the rigid tank B is of 0.4 meter cube with water at 600 kilopascal and 200 degrees Celsius. They are connected to a piston cylinder which is initially empty with closed valves. So this is the arrangement which is given. We have two tanks which is connected to a third tank which is a piston, and all are closed, and tank A contains 3 kg of water at 120 degrees Celsius, and the volume is 0.6 meter cube, and similarly B is 0.4 meter cube and it is at 600 kilopascal and 200 degrees Celsius. So the pressure in the cylinder should be 800 kilopascal to float the piston. So the piston will only float when the pressure is exerted on the piston is 800 kilopascal. That's when the piston will start moving. So now the valves are slowly opened and heat is transferred, so the water reaches a uniform state at 250 degrees Celsius with the valves open. So find the final volume and pressure and the work and heat transfer in the process. So what will be the final volume, pressure, and the work and heat transfer during the process. So what will happen is this is the process which will take place. So you have initially some volume, the total volume when the valves are open. So the piston will not move initially. So the heat is added and water starts boiling. So it will go to state 1A till 800 kilopascal where the piston will start moving. After that point your pressure will remain constant because at any point your force will be balanced. So the pressure will be constant and the volume will expand. So it will go from 1A to 2. So that are the two processes which will happen. So initially you open the valve, all the valves. So it will come to an uniform state and you are adding heat. So gradually a pressure will rise and it will reach pressure of 800 kilopascal where the piston will start floating, and from that point on your pressure will remain constant and the volume will change. So initially volume is constant till the pressure is 800 kilopascal, and the second process the pressure is constant and the volume changes. So you have two process of V equals constant and P equals constant. So this will see how to solve this. So applying a control volume across all three tanks. So the total mass is constant since nothing is going out. So the total mass is m2 minus m1. So m1 is the mass in tank A and mass in tank B. And applying the first law for this, we get u2 minus u1, which is equals to q minus w. So we need to find first the work done. So since this is happening in two process, so first when the volume is constant till it reaches the pressure of 800 kilopascal, there is no work which is being done. And once it has reached 800 kilopascal and the piston starts moving, there is a work which is generated in pushing the atmosphere. So it's doing work on the atmosphere. So which is happening at constant pressure. So that is your P into delta V. So we need to find out what is the final volume to estimate the work done. So we know the pressure, but we need to find out what is the final volume to find out the change in volume. So to do that, first we'll find out what is the initial volume. So initial volume is we know initially the tank A is at 0.6 meter cube and 3 kg. So the specific volume for the first tank is 0.2 meter cubes. So using that, the dryness fraction comes out to be for this condition of 120 degrees Celsius, we estimate using the saturated liquid and saturated vapor specific volumes, the dryness fraction it comes out to be 0.223327. And similarly, the internal energy at that point comes out to be 955.89 kilojoule per kg. And for tank B at the initial state 1, yes, specific volume is 0.35202. So straight away from 600 kilopascal and 200 degrees Celsius. So mass of water in tank B comes out to be 1.1363 kgs. So and the internal energy straight away from for 600 kilopascal and 200 degrees Celsius is 238.91 kilojoule per kg. So the total mass now is 3 plus 1.1363, so comes out to be 4.1363 kgs, and the volume will be uh, the volume occupied by A and the volume occupied by B, which is 1 meter cube. So volume and B will be 1.1363 multiplied by specific volume 0.35202. So the and you know the initial volume in tank A, which is 0.2. So that will come add up to be 1 meter cube for the total volume in tank A and B. So we know volume at state 1, which is 1 meter cube. Now we need to find out volume at state 2. So to find out volume at state 2, which will be the volume of tank A plus B plus C. So we need to find out what is the change in volume of tank C. So that is straight away the change in volume. So for this we know at state where the piston starts moving at 1A, there my pressure is 800 kilopascal. So 800 kilopascal, the specific volume is the total volume divided by the mass, which is 0.24176, because the volume is specific volume is constant across this line. Because mass is constant, your volume is constant, your specific volume will be constant. So the total volume divided by the total mass gives you 0.24176 meter cube per kg. So that's specific volume. So at 800 kilopascal and specific volume of 0.24176, my temperature is 173 degrees Celsius. So if you assume at 800 kilopascal and 250 degrees Celsius, your volume is 0.29314 meter cube, which is greater than V1A. So we know the final temperature of the gases, which is 250 degrees Celsius. So the final temperature is 0.29314 meter cube, which is specific volume. So from there we can find out what is the volume at state 2. So mass into specific volume will give you 1.2125 meter cube. So that is the final volume. So the final state is 800 kilopascal and 250 degrees Celsius. So correspondingly, internal energy is 2715.46 kilojoule per kg. So the change in volume here is 0.2125 multiplied by your pressure will give you the work done. So work done comes out to be 170 kilojoules. Now heat transfer will be your change in internal energy plus the work done. So change in internal energy is M2 U2 minus the final total internal energy minus the internal energy of contents in tank 1 and minus internal energy in tank 2, tank B, plus the work done. So substituting the values, we get 4.1363 is the total mass multiplied by the final state internal energy at 800 kilopascal to 50 degrees Celsius, minus 3 is the mass in tank A multiplied by for the initial condition of 120 degrees Celsius. We found out the for two phase case what is the internal energy, which is 955.89, minus the mass in tank B, which is 1.1363 multiplied by the internal energy in tank B, which is 2638.91, plus the work done, which is 170. So the heat transfer will be 5536 kilojoules. So that is the total heat which is being transferred to the system. So next question, I have 4 kg of air which is contained in a vertical piston cylinder assembly. The piston weighs 50 kg and has a face area of 0.01 meter square. The air initially occupies a volume of 0.05 meter cube. The air now undergoes a process wherein its volume decreases to 0.0025 meter cube and 1.41 kilojoule of heat is lost to the surrounding. Determine the change in the specific internal energy of the air. So you have 4 kg of air which is contained in a vertical piston cylinder assembly is shown. So you have 4 kg. So the piston mass is given to be 50 kg and area is also given as 0.01. So we can estimate the pressures. So the air initially occupies the volume. So initial volume is given to be 0.005 meter cube. So they say air is undergoing a process wherein its volume decreases to 0.0025 meter cube and 1.141 kilojoules of heat is lost to the surrounding. So heat is also given, how much heat is lost. So we need to find out how much the internal energy is changed during this process. So first is what we'll do is we need to estimate the work done. So if you apply first law for the system here, what we know is we need to find out the specific internal energy of the system. So what we know is how much heat has been lost. We have no idea on what is the temperature of the air initially and what will be at the final state. So only thing what we know is what is the change in volume and how much heat has been transferred. So we need to estimate the work to apply in first law to the system. So we can estimate delta U will be Q minus W. So we know Q, we need to estimate W to estimate to find out what is the change in internal energy. So if you write the work, so there are 3 parts to this work. So one which is the work done on air, and the work, since the piston has mass, so there is some work which is done by the piston, and this is the system, and then there is surrounding which does work. So the total work will be 0. The system plus surrounding, the work done by system plus the work done by surrounding will be 0. So in this case surrounding is the atmosphere. So if you write, so W piston plus W air plus W atmosphere will be 0. So piston plus air, if you consider the system, atmosphere is the surrounding. So the summation of all this will be 0. So the piston, straight away we can find out what is the work done is the change in potential energy of the piston. So mass of piston into acceleration due to gravity into delta H. So delta H is delta V by A. So change in volume by area. So we know the initial volume, we know the final volume, divided by the cross sectional area which is given. So 0.005 minus 0.0025 divided by 0.01 gives you 0.25 meters. And then the work done by piston is 50 into 9.81 into 0.25, which gives you 122.625 joules. So that is the piston work. Then the atmospheric work is the pressure exerted by the atmosphere. So here we cannot find directly what is the air work which is being done, since we don't know what is the process which the air undergoes. If we know the process, we can find out the work done by air. Since we cannot do so, we have no idea how the states are varying. What we can do is we estimate the other works to find out the work done by air. So we have found out piston, and work done by atmosphere can be easily found out, since it exerts a constant pressure, and the pressure multiplied by the change in volume will give you the atmospheric pressure work. So the atmospheric work will be P atmosphere into delta V. So assuming 100 kilopascal is atmospheric pressure, we get 10 power 5 into 0.0025 is the change in volume. So 0.05 minus 0.0025 gives 0.0025, which comes out to be 250 joules. That is the atmospheric work. So the total work done on air is your minus, taking it the other to the other side, air and so atmosphere and the piston. To the right hand side we get WR is minus W piston minus W atmosphere. So since both of this is positive quantities, we get work done air is minus 372.625 joules. So this is the work which is done on air. So what actually means is the air is getting compressed and this much amount of work is done by piston and the atmosphere. So now applying the first law, we get delta U, which is the change in internal energy, is the heat transfer minus the work. So heat transferred is given as 1.41 kilojoules. So 1410 minus 1410 minus the work done is minus 372. So minus of minus positive, what we will get is minus the change in internal energy to be minus 1037.4 joules. But in the question what has been asked is determine the change in specific internal energy. So to find out specific internal energy, we have to just divide it by the total mass. Since the mass of air in the cylinder is given as 4 kgs, so minus 1037.4 divided by 4, it comes out to be minus 259.34 joules per kg. So next question, an insulated enclosure has air on both sides at 1 bar and 300 Kelvin. The two compartments are separated by a movable, conducting and massless partition. The spring having stiffness of 100 Newton per meter is originally undeformed. The cross-sectional area of the enclosure is 100 centimeter square. The initial length of the two compartments are 50 centimeter each. 1 kilojoule of heat is added with the help of an electric heater to compartment A. So doing so, we need to find out work done by air in compartments A and B, work interaction for the spring, and final states of air in the two compartments. So let's break it down first. So we have an insulated enclosure, we have air on both sides, and at 1 bar and 300 Kelvin. So both are at 1 bar and 300 Kelvin initially. So this both are partitioned using a movable, conducting and massless partition. So both can move and it's a conducting medium, so the heat can transfer. So spring constant is given. So initially it is undeformed and cross sectional area is 100 centimeter square. So and both compartments has equal volume. So since they are saying initial lengths of two compartments are 50 centimeter each, so that means initially both are at equal volumes. So first 1 kilojoule of heat is added to piston to compartment A. So doing so, what will happen is the internal energy of air in compartment A will increase. So its pressure will increase. So and it will also conduct heat to compartment B and will exert pressure on the piston, which will move the will compress or deform the spring. So these are the process which is happening. So with that we need to find out what is the work done by air in both compartment A and B, and what is the work interaction on the spring, and what will be the final states of the air. So first is, if we apply a first law for the whole process or the whole system, the container with both the compartments, what we will get is what we know is there is no work transfer out of the system. So W is 0. So only work interaction is between these two compartments. So there is no net work which is coming out because it's a rigid enclosure, insulated enclosure. There is no work which is coming out. So only is thing is we have heat transfer inside, which is by the electric heater, which is will be there inside. So there is only electrical work which is going in, but there is no heat transfer coming out. So only Q is 1 kilojoule which is going in. So this heat transfer will cause a change in internal energy of the system. So the change in internal energy will be Q minus W, W is 0. So change in internal energy will be 1 kilojoule, which is distributed between both the compartments A and B. So there will be delta UA plus delta UB, which is 1 kilojoule. So the initial volume before the heat is added, so both occupy the same volume. So we have 100 centimeter square of cross section area, and the length is 50 centimeter. So 100 into 50 multiplied by 10 power minus 6 to convert it into meter cubes, we get 5 into 10 power minus 3 meter cube. So that is the volume of compartment A and compartment B. And what is the initial mass of air in both the compartments is, we can get it from the ideal gas equation, assuming an ideal gas. So PV by RT is the mass. So initially both are at the atmospheric pressures 1 bar and temperature is 300 Kelvin. We know the volume now, and being air we know gas constant is 287. So substituting the values, the pressure is 1 bar, so 1 into 10 power 5 multiplied by 5 into 10 power minus 3, which is the volume which we estimated, divide by the gas constant 287, multiply by your temperature, which is 300. So this gives you the mass to be 0.0058 kilograms. So that is the mass of the air present in each of the compartments. So if we write a force balance on the partition, what we get is PA minus PB, which is K into delta X by A, is the total pressure balance, or you can write a force balance. So if you go back here, so there is a pressure exerted by air in compartment A towards the right. So towards right there is a force, so that is P of air in compartment A multiplied by area. So from the left what we have is the pressure exerted by the air in compartment B plus the force exerted by the spring. So that is K into delta X. So whatever the spring has been deformed to, so we assume the length of deformation to be delta X or compression to be delta X. What we get, the force is K into delta X, and the pressure from here is PV into the cross section area. So rearranging this, what we get, PA minus PB, which is K into delta X by area. So that's the force balance. Now what again is, we have the mass balance. So what the mass is present in area A and B will be same. So initially, so finally also it will remain same. There will be no change. So PAV by RTA equals PBVB by RTB. So gives PA is PB times VB by VA. So assuming TA and TP is same, because the partition is conducting, so both the compartments will be at the same temperature. So if we give it enough time, both will reach to a same temperature. So if you see the first case where the temperatures was constant and both were occupying equal volumes, so V and VB and VA is same. So what you get is P and PB equal same. So that's what we saw, both compartments to be at 1 bar and the spring to be 0. So PA and PB is 0 and you get delta X is 0. So that means the spring is undeformed. So that's what the initial conditions say. The spring is undeformed and both are at 1 bar. So that's what we see from this expression as well. So next is since delta X is greater than 0, so which says that PB is greater than PA. sorry, PA should be greater than PV. So what will happen is, this is the expression which we get. So now if the spring compression deformation is greater than 0, so that's where uh, if you are adding, only way is the spring can only deform. So you are adding heat to compartment A, so it will exert pressure on the piston and it will try to compress the spring. So delta x will be greater than 0. So if delta x is greater than 0, what we'll have is the volume at compartment A will be greater than the volume in the compartment B. So if that happens, volume of A is greater than volume of B, your pressure of compartment A will be less than the pressure in compartment B from this mass balance expression. So if that happens, pressure in compartment A is less than B, what it says is delta x is negative, which is contradictory. What we assumed is delta x is positive, but here it's coming out to be negative. So this is not possible. So the only way it can happen is when delta x is 0, so it remains undeformed, and whatever energy is there, it is shared by uh, both of the compartments. So essentially W spring becomes 0, and the net work done by each of the air is also remains 0, and whatever heat is supplied to air is conducted to the other compartment air also, and both will be at same temperature T2. So your change in internal energy will be half of the Q which is supplied. So delta UA and delta UB will be same. So going back here, delta UA and delta UB will be same. So it's 2 times of delta U equals Q. So delta U for each of the compartment will be Q by 2. So that will come out to be 0.5 kilojoules. So that is shared by each of the compartments. So this would have been not happened when the partition here is not conducting. Here it's conducting, so heat which is supplied to A, which also transfers to heat as heat to compartment B. If this partition would have not been conducting, in that case what will happen is the internal energy of A will rise, and it will exert pressure on B, and the spring will get compressed. Since it was conducting, the equations became contradictory. So the pressures volume increased and pressure reduced in the sense, and that caused the spring to be negative, but the assumption was the delta x is greater than 0. So this cannot happen. So it can only happen when the spring is not moving at all, the piston is not, the partition is not moving at all. So we started with delta x is greater than 0, assuming that compartment B is getting squeezed, spring is getting compressed, compartment B volume is reducing, compartment volume A is increasing. So that said, that with the assumption that delta x is greater than 0, and when we plugged it into the mass balance equation, what we saw is your pressure A is lower than your pressure B in compartment B. But if that happens, the force is not balanced, and that can only happen when the piston, instead of compressing, it is elongated. So which is contradictory to the initial assumption of spring compression which we made. So this too is not possible. Both satisfying the pressure balance and the mass balance equation is not satisfied, and it is only satisfied when the delta x is 0 or the partition is not moving. So that is the only condition where these two equations are satisfied, and that says both will have equal volume and equal pressure, and the temperature will also remain constant. and that happens, what is happening is whatever heat is transferred to compartment A, half of it is going in compartment B, so it is going as a whole system. So with that, we have finished what we have prepared for today questions. So we'll see such similar problems next week as well. We'll do some more problems on first laws for systems, and also more problems with respect to the two-phase systems, how it varies and so on. We also see some problems on refrigerants and waters and so on. And with that, I'll end the session for today. So that's it for today from my side. So see you next week.